last lesson, we were looking at the reflux setup. Okay, so the reflux setup is where you have your Liebig condenser placed vertically. The reason why we use reflux setup is especially important or useful for reactions with volatile compounds in it, okay, whether the reactants are volatile or the products are volatile. So what happens with volatile compounds? They will want to escape out of the setup. Okay, so what happens? The gas molecules will travel up as it reaches the condenser. Because the condenser is cold, you fill it with your tap water, so it liquefies. It turns into a liquid, and because of gravity, the liquid will naturally fall back into the system. So this way, volatile compounds will not be able to escape your reaction mixture until the end of your reaction, okay? Until you decided to stop the reaction and you're happy that you've completed the reaction, then only you can collect the products, okay? Right, so we have not, wow, really, we have not? Have you not drawn? Oh, we have, yes. I've drawn for you the SN1 and SN2 mechanism for with sodium hydroxide. It's the hydroxide ions, okay? It's basically the same as the mechanisms that you have drawn on page 4 and 5, okay? So just check with your notes. I will skip that part. The next one that I want to look at is the substitution with cyanide ions, okay? So cyanide ions is supplied in the form of potassium cyanide or sodium cyanide. So this is the structure of a cyanide ion, a carbon with a triple bond with nitrogen, and the lone pair comes from the carbon. It is important that the lone pair is on carbon because that's where your new bond will be formed, not on nitrogen. Okay. Now, if you notice that if I just draw this out, just to show you, you have a bromoethane, and then you react it with cyanide ion. Maybe I'll draw the full drawing. The potassium ion is just there as a counter ion. It will just float in the reaction mixture. So what happens? The cyanide ions will replace your halogen. In this case, it's the bromo that will get replaced. Fabian is just joining us. And you get this. Your other product would be the bromide ions. And again, the potassium ion will be there. But in this case, I'm just showing you the ionic equation. Now, what I want to point out to you is that initially you started with 2 carbons in your starting material. In your product, you get a molecule with 3 carbons. Okay, so this is an excellent reaction if you want to increase the length of the carbon chain by 1 carbon atom. Okay, only by 1 carbon atom. The reagent for this reaction is, as I mentioned just now, you can either use potassium cyanide or you use sodium cyanide. When they ask you to write down the reagent, please always write down the complete formula, okay? Instead of just writing down cyanide ions, right? You have to write down the counter ion as well. In this case, it's potassium or sodium, just like your hydroxide ions. When we look at the reaction of substitution of halogenoalkanes with hydroxide ions, it comes in the form of either sodium hydroxide or potassium hydroxide. Okay, now one thing that I want to highlight to you is that your potassium cyanide or sodium cyanide, your cyanide ions are dissolved in ethanol. It's not aqueous, okay? Please take note. The reason for this is because if you use aqueous, it's water. Water is actually a nucleophile. So you would get a mixture of products, okay? You will get cyanide ions attacking your halogenoalkanes, and you would also have water attacking your halogenoalkane. So to avoid this, you remove water altogether. You don't use aqueous cyanide ions. You use ethanolic cyanide ions, and usually this is written as ETH in bracket, just like how you would write down aqueous in bracket, but instead you've got ethanol. Okay, so from the product here, which is what we call a nitrile. Okay, so this is called an 1,2,3 propane nitrile. Okay, the prop is for the 3 carbons, including the carbon on C double bond N, and the nitrile is for the CN functional group. I want to change the color. Okay. Oh gosh. Okay. So from the product propane nitrile, what you can do is you can always convert this. Propane nitrile is hydrolyzed easily into carboxylic acid. So from there, you can change your carboxylic acid, whether you want to change it into something more reactive, you want to form esters and etc. So this is actually a great reaction. If you see in your question paper where you see that your carbon has been magically added 1 extra, that means cyanide ion was involved somewhere in the reaction. Okay. Right. Okay, the condition I forgot to mention that you heat it under reflux. Again, there's no other reason other than to regulate, to maintain the volatile compounds so that it doesn't escape from the setup. Okay, right. SN1 mechanism with cyanide ions. So we will not draw in your potassium or your sodium because they are just floating around in the solution. We're only interested in the cyanide ions. And for SN1, we usually use a tertiary halogenoalkane. So I'm just going to use bromine. Is there any specific? No, there's no specific. Okay. SN1 mechanism, the number 1 means that there is only 1 species in the first step, which is the slow step. Okay, so that means I only have the halogenoalkane in the first step. There's no nucleophile attacking yet. Okay, but I need to include all my dipoles, any charges, any lone pairs, and etc. So the first step involves the breaking of the carbon halogen bond, whether this is carbon bromine or carbon chlorine. And this is usually the first step of the reaction. Okay, so then you will form a carbocation. The positive charge is on the carbon, and because bromine gets the electrons from the bond pair, bromine becomes bromide. Okay, from a delta minus to become a full negative charge. Next is when your nucleophile comes in to attack. So it is important how or where you draw your lone pair of electrons is sitting on. Okay. Next is the nucleophile donating its lone pair to the positive carbon to form your product. The new bond being formed is between the carbon and the carbon. If you put your lone pair on nitrogen, the new bond will be between carbon and nitrogen, and that is wrong. Okay, so what happens to the charges? You have a positive charge combined with a negative charge, then you have neutral. You get a neutral product. So this is called a nitrile. Okay, so I wouldn't bother or stress out on the naming, but 1, 2, 3, so that's a propane nitrile. You've got dimethyl. Okay, 2,2-dimethyl propane nitrile, but I'll just leave it like that for now. Okay, the reason is because we're not even going to look at nitriles in A level. We're just going to be looking at it as a product like that. Okay, right. So the explanation is there, which by now at this point you don't need the explanation of the mechanism because it follows the standard steps for SN1 mechanism. Okay, your other product will be the halide ions. In this case, it's the bromide ions. Any questions so far?
No, miss.
Okay. Please let me know when you're done copying this down. Okay, Ayman? There is another thumb up, but from Isa and Eugene. Amy, thank you for the thumbs up. And Abby. So wait, the thumbs up means you're done copying or what? Oh, I get a love from Fab. Thank you. Can move on?
Yes, miss.
Thank you. The next one is SN2 mechanism. SN2 mechanisms are usually for your primary halogenoalkanes. Okay, so bromoethane. If the question doesn't specify, you just use the simplest halogenoalkanes. Okay, usually they will specify what they want you to draw. Okay, so always write down the polarity of your carbon halogen bonds. They're polar. SN2 mechanism means that there are two species involved in the first step or in the slow step. Okay, so the first species is your halogenoalkane, and the other species would have to be your nucleophile. And in this case, your nucleophile is again cyanide ion. The lone pair of electrons on carbon will be given or shared to the slightly positive carbon. So you form a transition state. A transition state shows you the process of bond forming and bond breaking. So that means they are in the process of being broken and in the process of being formed. Okay, then we usually draw this square bracket. One student asked me if that square bracket is compulsory. Well, it's optional and you will not be penalized if you leave it out. Okay, next, then you don't have to draw anything, actually, no arrows whatsoever. They will naturally form the products. So the new bond is between carbon and carbon. Again, you get a nitrile, and the other product is your bromide ion with the lone pair. So this is called N123 ethane, propane, propanitrile. Okay. So imagine if you use aqueous, you will have water. And water will also want to attack your halogenoalkanes. So that's why we don't use aqueous we don't use aqueous as the solvent, but we use ethanol as the solvent. Any question? Next, we will look at the substitution reaction of halogenoalkane with ammonia, which is another nucleophile, NH3. Please let me know when you're done. Okay, thank you for the thumbs up. Is that a green light for me to move on to the next slide? Okay.
Yes.
I'm guessing. All right, thank you. Okay, so this is how you name nitriles, but I've already given you the name. The carbon of the CN will be number 1, okay, because that's your functional group. So this is 1, 2, 3. So that's where you have a 3-methyl butane nitrile. Okay, moving on to this substitution reaction with ammonia. Again, ammonia needs to be dissolved in ethanol. So we do not want aqueous form. Okay, if I draw this out for you, where we have a bromoethane reacting with ammonia, NH3, and we know that the nitrogen is the one that owns the lone pair of electrons to form a new functional group called amine. What I want you to notice about this amine is that it has 2 hydrogens, whereas starting material, ammonia, you have 3 hydrogens. Okay, so that means there's an additional step. I'll show you what happens in the mechanism later on. Your other product would be bromide ion. Okay, so again, your ammonia will be dissolved in ethanol. You need excess. Okay, the reason why you need excess ammonia is because your product, we call this an ethylamine. So the ethyl comes from the 2 carbon, and the amine comes from the NH2 group. Okay, so the reason why your ammonia has to be in excess is because your product, your amine, has a lone pair of electrons there. And this lone pair of electron means that ethylamine can also act as a nucleophile. However, if you have a lot of ammonia, it will be like a competition. Ammonia will win because there's no chance for ethylamine to attack your halogenoalkane. Yes, it probably has a chance, but very, very small chance. Okay, so this is why it's important that ammonia is in excess, because the product of the nucleophilic substitution reaction, which is the ethylamine, can act as a nucleophile and attack another halogenoalkane to form a secondary amine, which is called a diethylamine. You can try at your own time when ethylamine is acting as a nucleophile. Yes, Mr. Fabian?
Miss, what happens to the other hydrogen?
Yes, the other hydrogen becomes a H plus. Thank you. I will show you how it becomes a H plus in the mechanism later on, okay? But thank you for pointing it out. The hydrogen from the ammonia initially will be removed and it becomes a H plus in the product, okay? Don't forget to copy this down as well. Okay, because the product can act as a nucleophile and then it can attack another bromoethane. Usually I would show students the mechanism, but I don't know why I don't bother this time. Please let me know when you're done. And then I will show you the SN1 and SN2 mechanism. The steps are similar, except there's one extra step. Okay, Ayman, just give me a thumbs up, or is that from just now? I'm guessing that's a green light for me to move on. Okay, let's draw the SN1 mechanism for ammonia. So SN1, again, it will react with a tertiary halogenoalkane. So that's CH3. I will use bromine. Okay, so SN1 means only one species is involved in the first step or the slow step or the rate determining step, which is not your concern at the moment. Okay, don't forget your dipoles. The nucleophiles don't come into attack just yet, so that means I must break the bond. So I have CH3 and I form a carbocation. And that's when my nucleophiles come to attack, which is NH3. Okay, the lone pair on the nitrogen will be donated to the positive carbon to form almost my product, but not just yet. Okay. Hold on, yeah. Okay. So what happens when nitrogen has donated the lone pair to carbon, nitrogen will now develop a positive charge. Okay. Also, another hint for that is because nitrogen has 1, 2, 3, 4 bonds. So it becomes positively charged. Next step, how do we remove that positive charge? We can't just remove it simply, okay? One way is that the electrons from the nitrogen-hydrogen bond will be donated to the positive nitrogen, okay? So it becomes this. So you're left with 2 hydrogen, and the nitrogen has its lone pair restored. First, it gave away its lone pair. Remember, 2 carbon, okay? And then because it gave away its electrons, it becomes positive. Carbon will become negative, which cancels out anyway. And then, in order for nitrogen to lose that positive charge, we supply it with electron pairs from one of the nitrogen-hydrogen bonds. Okay, so that hydrogen lost its electron, it becomes H plus. Don't forget your bromine, which gains an electrons. Sorry, gain a pair of electrons, it becomes Br minus. So that is how or where the hydrogen from the ammonia went to. It becomes a hydrogen ion in the product. Okay, and because of this, your amine product can act as a nucleophile. This is still considered a primary amine. Okay, how do you identify your amine? You look at the bonds that are attached to the nitrogen. You have one alkyl group, one big alkyl group there attached to the nitrogen, and the rest is the hydrogen, and the rest are hydrogen, sorry. So this is primary amine. Ammonia is actually an amine as well. It's a primary amine because all the 3 bonds are attached to hydrogen. Okay. Any question? Okay, good. I would like to finish the SN2 mechanism just before we go. We've got about 10 minutes left. Okay, right. So for SN2 mechanism, we're going to use bromopropane. So I usually use the same example, but you know that this can work with other halogenoalkanes as well. Okay, so SN2 mechanism, complete your diagram with the dipoles, and the 2 in SN2 means that there are 2 species involved in the first step. So that means the nucleophiles should come into attack. Sorry, it's not oxygen. Should be ammonia and H3. Okay, lone pair must be drawn. The lone pair is donated to the carbon, slightly positive carbon. The carbon-bromine bond breaks and the electron is given to the bromine. You form a transition state. Carbon-bromine bond is in the process of breaking. Carbon-nitrogen bond is in the process of making. Again, if you want to draw the square bracket, it is optional. Next, in the transition state, you don't have to show any bracket. It will naturally, the bromine will naturally leave the group and the carbon nitrogen bond will be formed. But remember, you still have 3 hydrogens here, so you must have that positive charge on nitrogen. Okay, so this is something that's always almost forgotten all the time, the positive charge on nitrogen, because there are 4 bonds on nitrogen, and you know that nitrogen can form 3 bonds. Well, it can form 4 bonds, but not in its natural state, not in its neutral state. Okay, so what happens next? You don't want to end up with a product with a positive charge. One of the nitrogen-hydrogen bond breaks. Both the electrons go to the nitrogen to form what we call an ethane nitrile. With the lone pair. So this ethane nitrile also can act as a nucleophile, and if it comes in contact with a halogenoalkane, okay, another molecule of bromoethane, then it can always attack. So that's why we want to have a lot of ammonia molecules in excess so that they win the competition. They have a higher chance of attacking the bromoalkanes compared to the amine products. Okay, so that is all. If you don't have any questions, you can